Is he tall?
Is he fat?
What about
How's everyone doing?
fantastic?
All right. Okay, first start out with a couple of administrative things. I have the second mini exam. So the due date on this one is the 18th. Remember, these are, you do them if you want to do them, but you have to do 3 by the end of the semester, right? Was it 3? I think it's 3. Yeah. The syllabus will clarify. Now, on the first one, I had some brave souls do the first one, and I'm going to allow those people to turn in a fourth one. So in other words, the people who actually went and tried to do the first one were like the guinea pigs, all right? And they get a chance to do an extra one, all right? And the reason why is because you kind of get a feel for how I'm grading these. And so some of them are going to get them back and realize that, you know, a problem was completely wrong. And so the lesson from that is these problems are supposed to be a little challenging. If you have any question about what you're doing, you need to get with me, right? I want you to come visit me and talk to me about these tests. That's kind of like, I want to see how you think. I want to see how you approach problems. And, all right, does that make sense? Okay. So I'll pass these out. Paul, these grades are posted online. Ricardo? Adam? Rose? Audrey? Chad? Ernesto? Paul or Ernesto? No? All right, so now I'm not providing the answers to those right now. So if you want to know what the answers were, you want to talk about why it's wrong, you come talk to me, all right? Anything else? Questions on any of this stuff? Mini exams? No? Okay. So basically, the people who turn that in, if you didn't get a good grade, it's okay. I'm going to let you turn in another one, all right? If you have not turned in a mini exam yet, you do not get that, all right? You have been warned. These problems are supposed to be a little bit challenging. Don't wait till the day before they're due, right? Those of you who did that first one know that you should probably not wait till the day before. And let's see, I'm looking at this second mini exam. It's 5 questions. Hopefully you'll be able to finish this off, or you'll be able to do this one hopefully by the end of next class. All right? In other words, we will have covered all the topics. Yes?
On there, given the point, it says we can find the shortest distance. What is it supposed to say?
Where? Oh, yeah. We can find the shortest distance.
Oh, just that?
Yeah.
Okay.
We can find the shortest distance. All right, so we did last class, we ended with this really nice example where we were able to find the shortest distance between a point and a plane, right? That's what we did. But the example we did, we actually found the shortest distance, or the distance between 2 parallel planes, right? So our example was a little bit different than the note that preceded it, but the technique was pretty much exactly the same. Pick a point, or you have your point, pick another point on the plane, draw a vector, get your normal vector, project it onto the normal, blah, blah, blah. Get the component. Okay, you can look back and review that on your own. All right, today we're going to finish this section off, and we're going to be now trying to find the shortest distance between a point and a line. So we have a line sitting in 3-dimensional space, or 2-dimensional space, but in this case, let's just look at 3-dimensional space. We have a point. Let's say the projector or the camera there is a point. So the question is, what is the shortest distance between that camera and this line. So that line goes over there and goes back this way. What's the shortest distance, right? So the way to do this, there's a nice geometric way to set this up. I'm going to do it in two-dimensional space so it's easy to see. First thing you're going to need to do is pick a point on the line, right? Call it Q. Then get some other point on the line. So you need to have at least 2 points on the line so that you can then create a vector that goes from one point to the other, all right? So we are given a point and we're given a line in three-dimensional space. We have to find a vector on that line. That's basically the first step. Find a vector on that line. Then, once we find that vector, we can create a new vector that goes from any single point on the line to the point we're given. We'll call that vector B. And then we're interested in knowing the distance from here to here, like a perpendicular, right? So this is really a right triangle. So we want to know what D is. All we have are two vectors. Vector A, which lives on the line, and vector B, which goes from any point on the line to the point we're given. So the way we can get this is by using this formula. Just drawing a right triangle, realizing that theta is the angle between these vectors, right? So theta is the angle between A and B. And the formula is that sine of theta is equal to D over the magnitude of B. So opposite over hypotenuse, opposite over hypotenuse. The magnitude of B is how long this hypotenuse is, right? So does everyone agree with that geometric description? Yes? And you can solve for B, can't you? I mean, sorry, solve for D, right? Multiply both sides by the magnitude of B. Yes? So I'm going to write that down right now. D is equal to the magnitude of B, right? Sine theta. Now, when you look at this, think about the problem. Someone's going to give you a point, right? And they're going to give you a line. And in order to find the shortest distance between the point and the line, D, we need to know the magnitude of B, which would be from any point here to there, that length, right? Then sine of theta. But what's theta? Theta is the angle between these two vectors, right? And do we have a formula for finding the angle between two vectors? We do, right? But that seems like it's going to be a little tedious, doesn't it? Doesn't that seem tedious? So, does anyone recognize this formula? I mean, this formula is just that right there is very close to something that we've seen.
Component cross product?
Cross product. Cross product. Now, let's go back in our notes and look at it. Cross product was 10.4. Up, there it is. There we go. Let me make this a little bigger for us. Look at this formula. This formula says that the magnitude of the cross product, so be careful there, magnitude of the cross product is equal to the magnitude of U times the magnitude of V times sine of the angle between the two vectors, right? So that looks really close to this, except we're missing out here like this other magnitude of some vector. Agreed? So watch what I'm going to do. I'm going to make it appear. Now, what's the only other vector that we have when we were messing with this picture here a second ago? What's the only other vector? That vector A, right? That vector A was the only other vector we have. And we're talking about the angle between them, right? So I'm going to introduce the magnitude of vector A here. So watch. D is equal to the magnitude of vector A, magnitude of vector B, sine theta. But I can't just throw a magnitude of A in there, right? I can divide by it also. Right? So now that's really like me introducing a 1. But now the numerator is really what? What's the numerator? It's the magnitude of the cross product, right? Of A and B. That's the definition of the numerator now, but then divided by the magnitude of A. And voila, we have a formula for D that doesn't require that we ever find theta. right? All we have to do is be able to do the cross product of these two vectors, right? Do the cross product, take its magnitude, and then divide it by the magnitude of this vector. And we're done. We have that will give us the shortest distance between the point and the plane, or point and the line. That's pretty nice, isn't it? Now we have to have come in and put that little magnitude of A over magnitude of A to do it, but once you see it done, it's not that big of a deal, right? Just throw that in there. All right. So, see if anyone can see into the future here. Where do you think, if I'm talking about a line that's sitting in three-dimensional space, right? Where do you think I'm going to get vector A from? I mean, I could just use 2 points and create a vector, right? But if I'm given the actual vector equation of the line, right? What's the vector equation of the line? Go ahead.
You could use two arbitrary values for t.
Okay, so you're saying use 2 values of t to get 2 points, and then create the vector, right?
Yes.
What I'm saying is, if I give you the vector equation of a line, right? If I give you the vector equation of a line, it's actually going to look like this. R of t equals R naught, right? Plus tv, right? And what is v? A direction vector, right? Which means that vector v is on this line, right? So wouldn't that vector v qualify as A here? Wouldn't it? Any vector that points in the same direction as this line would work for A. Remember, how do we get v? We get v by taking 2 points and subtracting. And that's how we get it. So if someone gives us the vector equation of a line like this, we don't even have to go find A. A is v. Make sense? All right, let's see what this first example looks like. I think the first example, I give us, shortest distance between, there we go. So find the shortest distance between the point 3, 6, negative 7 and the line through those 2 points. So I give us a point here, 3, 6, negative 7. I give us a line sitting in three-dimensional space that goes through these points, 0, 3, 5, and negative 4, 9, 10. Right? Do you all agree with that picture? And I'm trying to find the shortest distance between them, which would be like if you drop a perpendicular straight down here, right? I'm trying to figure out what that is. We'll call it D. So what is that shortest distance? All right, so what do we need in order to do this? Good. We need to create a vector that goes from either point here to the point that we're trying to find the shortest distance to. So let's go the vector from here to here. Let's put that in there. And what is that vector, Edward? Wait, do I have the right class here? Wait a minute. Shoot, never mind. Somehow my sticks got mixed up. How did this happen? Not Edward. Quentin.
Yes.
What's the vector from 0, 3, 5 to the point 3, 6, 7?
Negative 4 minus 0. So
Wait, this one right here from here to here. Yeah, I'm going that one.
3,
3,
3,
3,
negative 12.
3, 3, negative 12. Do you all agree? Yes? I'm not even looking at the numbers, so.
So that line you do for D, is it always going to be a right?
It'll always be perpendicular to your line. Like the shortest distance should be the straightest line to the, straightest path to your line, right? And that's got to be perpendicular to it then. Okay, now in the formula we were using a second ago, that's vector B. All right, that was vector B. So vector B is this one. Now we need another vector, which is the vector that goes from this point to this point, right? So that was vector A in the formula. Jonathan, vector A is -4, 6, 5. Okay. Now, the formula that we just put up on the board a second ago was D was equal to the magnitude of what? Cross product of A and B, right? Over what though? Magnitude of A. Now you can't mess this up. You can't put magnitude of B here. It has to be magnitude of A. The magnitude of A is the vector, or A is the vector that's on the line. All right. So we need to get a cross product first, right? So let's do our cross product. Let's do A cross B here. And to do that, I'm going to do the vector -4, 6, 5, stack it on top of 3, 3, -12, like that. And then we just do our little thing where we cover things up and calculate. So why don't I give you a second to do that. Has anyone figured out how to do cross products on their calculators yet? What calculator is that?
TI 36X Pro.
So it lets you put a vector in and cross them? Like it actually has a cross product feature?
Yeah.
Okay, cool. All right, so why don't you tell me what you got?
I got something big. I got, for the whole vector, I got...
Oh, did you already do the magnitude or just, what's the vector itself?
I got the vector itself.
Okay, what's the vector itself?
The vector itself, I got 87,
Uh-huh.
33, 30.
33, 30?
Yes.
Anybody else get this?
Yeah, I got that too.
Okay, so we got a couple of people in the room that agree, then we'll go with it, okay? So, oh, did you have those backwards? Did you have those flipped? No?
No, I didn't.
Let's see, yeah, hold on.
Oh, maybe.
So, yeah, you know, it's okay, because remember, if you do the cross product the other direction, the other order, the only thing that changes is the sign, right? Now, will that matter?
In a moment, I don't think that.
It won't matter in a moment, because what are we going to do? Take the magnitude, which is the length of the vector, which won't matter, because one's pointed one way, the other's pointed the other. So if you have negative, 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 that's fine.
Well, the middle one's positive, no?
I don't know. I haven't done it.
No, because you got to flip.
Remember, the middle one, you always have to change sign. Yeah. All right, so are we okay with this? You all right? Okay, now I need the magnitude of this, which means I have to take the square root of 87 squared plus 33 squared plus 30 squared. And did you get that as a decimal? Can you give me that as a decimal?
97.77.
Let's go with that. Okay? And now I need also to use the formula, I need the magnitude of A. So I'm just kind of getting all my stuff here. Magnitude of A is square root of, let's see, -4 squared plus 6 squared plus 5 squared. And let's do that as a decimal also. 8.77. And so the distance between them, the minimum, the shortest distance between that point and that line is 97.77 divided by 8.77, which is approximately 11.50.
50.
15?
Yeah.
Okay, 11.15. Anyone second that?
Yep, I second.
Okay. All right, there we go. And this is our answer doesn't have any units on it. It's a unitless, I mean, it could be feet, miles, centimeters, whatever unit we're measuring in. I still find this pretty amazing. I mean, we are calculating the distance between a point in three-dimensional space and a line in three-dimensional space, right? And the only thing we had to do was arithmetic to do it, right? I mean, square roots, okay, yeah, that's a little bit complicated, but there was no cosine, no theta, no angles, right? No trig functions. All cross products and magnitudes. All right, so that is the main result there. I think I have the formula. Do I have the formula? Yeah, it's down here. So there you go. That's the formula in the notes right there, the distance. And then we did our example. And that is it for 10.5. We're ready to move on to 10.6. Now this section, just so you know, is going to be, it's going to actually go pretty fast, this section. We can really bog ourselves down in here with this section, but I'll kind of give you my philosophy on this. What we're trying to do is have a basic idea of what certain equations look like. So like, you know, from college algebra, if you write y equals mx plus b, or if you write like ax squared plus bx plus c, or if you write like e to the x, or you know, we have sine x. Like you look at these things. You know, this is a line, right? This is a parabola. This is an exponential function. This is a sine function. We have a basic idea of what they look like, right? That's exactly what we're doing here, but we're doing it for surfaces in three-dimensional space. Okay? That's what we're going to work on. Now, you're already familiar right now with two types of objects that live in three-dimensional space. Lines, right, which have the equation r of t equals r naught plus tv, right? We did that. And then planes. And planes look like ax plus by plus, yes, c. We did that last class. You had the standard form for a plane. So lines and planes in three-dimensional space, we've got. Now we look at this other thing, these other things called cylinders and quadratic surfaces. And we just want to be able to recognize, oh, the equation, oh, that should be a cone. Oh, the equation, oh, that's a ellipsoid, right? It's just pattern recognition. So there's not a whole lot of theory behind this, I guess I should say. So we're going to start with some things in two-dimensional space that you should recognize. And I am going to kill the lights because I think it'll be easier for you to see what's going on here. Good night. So back in two-dimensional space, right? Two-dimensional space, the equation x squared plus y squared equals r squared was a circle. And if you change r, you just get a different radius circle, right? Blah, blah, blah. We've done that. Great. Now, in two-dimensional space, if your equation changes to x squared over a number squared plus y squared over a number squared equals 1, you no longer are looking at a circle. You're looking at an ellipse. And depending on how you change the numbers underneath, a and b, you're either going to get an ellipse that is wider than it is tall, or you're going to get an ellipse that is taller than it is wide. And that's all dictated by these two numbers, right? Those are your ellipses. Then, in two-dimensional space, if we change the formula for an ellipse by just one little thing, if we change that to a minus instead of a plus, you no longer have an ellipse, you have a hyperbola. And you have something that looks like that. So here's the equation down here. And if I change a and b, it does change it, right? But all of these are hyperbolas, all right? So we should recognize those formulas from conic sections back in pre-cal or college algebra. Now we get into cylinders and quadratic surfaces in three-dimensional space. So all of the equations that we just looked at, I want you to notice that equation has two variables in it, x and y, right? Now a and b would be given to us, but x and y would not. So x and y here are variables in the equation. We have an equation, right? Same with ellipses, two variables in the equation. Same with circles, two variables in the equation. When we're looking at three-dimensional space, equations involving x, y, and z, three variables, right, are all going to be surfaces. If we see x, y, and z in the equation in three-dimensional space, we are going to be working with some sort of surface. Now, before computers, right, in 3D imaging, mathematicians had to try and graph them by hand. And to do this, we use what are called traces or trace curves of the surface. All right, so I'm going to try and do a problem right now showing you trace curves, and you'll appreciate how it's great to have technology nowadays. All right, so let's say I want to draw this by hand. All right, now the important thing is that if we live in two-dimensional space, what is that? A circle. But I'm telling you we live in three-dimensional space now. All right? I'm in three-dimensional space, not two-dimensional space. So let me try and draw this. Let me go this way. Okay, let's say this is x, this is y, this is z. All right. So remember that equation, x squared plus y squared plus x squared plus y squared equals 9, is just the equation of a circle in 2D. But now in 3D, what does it become? So it's all the points. Basically, this right here are all points x, y, and z, right? Which make the equation true. Can somebody give me an example of a point that would make that equation true? Give me a point, an x, a y, and a z that would make that equation true. 330. How about 300? That okay?
Yeah.
So if I replace x, so remember this is x, y, z. So if I replace x with 3, I've got 9. Plus, if I replace y with 0, I've got 0. That's already 9 equals 9, right? It's already true. And that really doesn't matter then, does it? So you could continue, you could say like 301, right? You could go like 30-1. In fact, this coordinate, the z coordinate here, is completely free, isn't it? And so we call it a free variable. The z in this equation is a free variable. It can be anything we want it to be. It has no effect, no impact on the picture. So imagine we fix our z to be 0. And then we try and come up with all the different ordered pairs x and y that would make this true. All the x's and y's that would make it true would draw a circle, wouldn't it? But our z would have to be 0. And z being 0 in three-dimensional space means you're where? The xy plane. Right? Z is 0, up and down is 0, means I'm on the xy plane. So in this right here, I'm basically going to draw a circle radius, what's my radius? Radius 3 in the xy plane. So in my picture, imagine I have like 3, 3, negative 3, negative 3. So that's my xy plane on the ground. And I would just draw a circle that would be on the ground. Y'all see that? That's called a trace curve. What it is I'm fixing z to be 0. All right? So it's like this. What I've done is I said, let z be 0. And then I sketched whatever the equation was. X squared plus y squared equals 9. Now let me do another trace curve. Let's let z be 1. And now let's sketch x squared plus y squared equals 9 again. So what's that going to do? What's it going to do?
Move the whole thing up.
It's just going to take that whole circle and move it up. See, the only thing that's changing is all your z coordinates are now 1. So every point that you had there now just moves up 1. So you get this second curve that lives 1 unit above this. Right? Everything's moved up 1. And then I could do another trace curve. Like maybe I do like let z be 5. And if I let z be 5, then I'll have something up here, won't I? Now imagine letting z change, like go through all values, positive and negative. What are you going to draw? A cylinder, right? So this is going to come down like this. Now it's going to be a cylinder that extends in each direction forever, won't it? It'll go up the z-axis and down the z-axis. Yes? So this sort of equation where we have two variables, right? Out of the three, we have two. Squared plus the other variable squared. So two of the variables squared and added together equals a constant. That's going to be a cylinder. Now that cylinder does not have to go up and down. It can actually go left and right. And what's going to dictate that is whatever variable is left out. So like right now, which variable is free? Z. So our cylinder travels like parallel to the z-axis. Do you all see that? Now what if we wanted to graph this instead? Y squared plus z squared equals 9. Now your cylinder is going to go down the x-axis, right, instead. So it would actually be coming out of the page, like into the page, so it'd look like this and go back in there, right? You'll see that? And then what if I did, what's the only other thing I could do here? X squared plus z squared, and that would leave your y free, and that would go this way, wouldn't it? Okay, so the idea of the trace curves is really good if like we don't have 3D software to visualize things. So I want you to kind of visualize these trace curves a little bit different. Just slightly different. So I need to kind of erase this to kind of show you what I mean by that. Let's see how this works. I don't know how this is going to work with your brain or not. You know, we'll see. So let's go back to the beginning of this problem. Let's kind of act like we didn't know what this looked like, right? And what I tell you is that I'm going to fix z equal to be 0, all right? Now z equals 0 is the xy plane, right? So I want you to imagine coming through, and I'm telling you that when you take this solid, or not this solid, this surface, when you take this surface and you slice through it, if you slice through this surface on the xy plane, you cut through the surface, it forms that circle, right? Then it's like you're taking a slice through and I tell you, oh, it's a circle. Then I say, okay, move your blade up and slice through again, and I tell you it's a circle again, same size. And then move your blade up again and slice through again, and it's the same circle. Can you see that if you kept doing that you could start to visualize that it's a cylinder? Slices that all look like circles, they're all identical? Okay, that's what my visualizations from here on out are going to be about. So I'm going to go back to this. Here's the cylinder, right? This cylinder would have the equation what squared plus what squared equals what squared? X squared plus y squared equals some r squared, right? Some radius squared. We all agree with that? Now, if I look at the traces, if I cut through, where are my traces? I have to show them, hold on. Show trace curves, there we go. So you see that blue ring? All those blue rings are what I get when I cut through like this, right? If z is 0, I'm cutting through. If z is 1, I'm cutting through. So I get these circular traces, right? Now, cutting through with something like z equals 0, that's one thing I could have done. But why not try then to cut through with a blade that cuts this way instead? Right? So let's imagine we're in our room, x-axis, y-axis, z-axis. We already said if I cut this way, that's like z equals 0 or z equals 1 or z equals 2. But what if I cut this way, like this? What's that? So what plane is that I'm cutting parallel to? That's the x, right? That was x in our room? X, z, right? So I'm cutting through with something like this, xz. Yes? Okay, if I'm saying xz plane, then what's being held at 0? If I cut this way, xz plane, what's being held at 0? Y, right? Y would be 0? You following me? Okay, so if I slice it with the xz plane, so cut with the xz plane, another way to say that would be to say cut with y equals 0. So we're not saying z is 0 this time, we're saying y is 0 this time. And I want you to see what happens. Let's say that this is the equation x squared plus y squared equals 9, the one we had earlier. If I'm going to cut with the xz plane, in other words y equals 0, then what does this become? X squared equals 9, which means x is equal to plus or minus 3, right? So look at this. Which plane are we doing? XZ plane. If I cut through, there we go. If I cut through, why won't it won't let me go to 0? Damn it. Shit, it's not letting me go to 0 on my code. I need to go fix that. This is that plane that I was telling you, the XZ plane, right? If y is 0, then see those two planes? It actually becomes one plane in the middle, right? If I cut through, I'm going to hit at that blue line. Do you agree? Those blue lines are where I hit, right there and right there. And how is that connected to this? If I turn this sideways and look where those blue lines hit, like where are they hitting? At x equals 3 and negative 3, right? This is your x-axis now. So it's hitting at 3 and negative 3. Does that kind of make sense to you? I need to change the radius of this thing for it to correspond to this. But the way I want you to see it is, if we cut this way, right? It had no impact on this equation. And we were left with circles, because that's a circle. But if I cut this way, it does have an impact on that equation. I'm left with x equals 3, which is held constant. And so you have this vertical line. Or if you'd like, you can say like a plane. Does that kind of make sense? Now, what if I want to cut the other way with this plane? This is the YZ plane, right? If I cut the YZ plane, here it comes. Now they're coming out at you. Do you see that? Your YZ plane. So we have a combination of 3 different types of planes we can slice our object with. We have a plane that is parallel to the XY plane, the ground, a plane that is parallel to the XZ plane, and then a plane that's parallel to the YZ plane. And the object that it creates when I cut through is, in this case, either a circle or a line. Do y'all see that? Sure? All right, because the objects are going to get more complicated now, all right? Okay, so some things to note about, if we change the variables, we get different cylinders. Yeah, so this is what I was just telling you. Like this one right here, this is a cylinder, so the equation was x squared plus z squared is a constant, right? Y is free, so it's going to go down the y-axis. So cylinders look like this. This is the equation of a cylinder in 3-dimensional space. All right, now let's go on to the next type of surface that we want to be familiar with, and that is something called a parabolic cylinder. So traces, if I go back to cylinder, This is the cylinder, like the Coke can that we just looked at. Traces are circles and lines. Cut this way, circle. Cut this way or this way, lines. Yes? Okay. The way we define a parabolic cylinder is that traces are parabolas and lines. So cuts are either going to give us parabolas or lines when we cut through. It's hard to visualize that, right? Or do you already kind of visualize it? There's a parabolic cylinder. It's a piece of paper folded up, big deal, right? That's all it is. So what's the equation of a parabolic cylinder? It's just the equation of a parabola, isn't it? Like y equals x squared. Now we do have a constant in front because that can affect, how does a constant in front affect the parabola? It's going to be opened up, it's going to stretch it or flatten out. If this becomes negative, then what? Flips it over to the other side. So if I make adjustments to the leading coefficient, it's going to flip that over like that, right? Make sense? Now, here, y is free. And since y is free, do you see that that paper kind of goes down the y-axis? So you could say that in the xz plane, if we look at it, like if we position ourselves so we're standing way down on the y-axis, way down at infinity, and we look down, we've got parabolas, right? Okay, but let's look at the traces. Let's look at the cuts. So let's say I cut through with something like the xy plane. What am I going to get when I cut through with things that are like the xy plane? I'm hearing lines and parabolas. So I'm cutting through with something that's parallel to the ground. Cut through. Lines, let's see them. XY plane, here we go. So I'm cutting through with this. Here they come. So I'm cutting through. Why is it not wanting to move? There we go. So I cut through. Where do they intersect? Right there, right? Cut through. Those are lines, aren't they? So when I'm cutting through with something parallel to the XY plane, I'm getting a line. Now, what if I cut through with something parallel to the XZ plane, which would be this plane? Start slicing. Yeah, then you're going to have your, there's that plane. See it cutting through like that? Slices through, and you get these parabolas. No matter where you move that plane, as long as it's parallel to the XZ axis, you're going to get parabolas. So that's why they say a parabolic cylinder, the traces are either lines or parabolas. We could switch it up. Okay, so this one right here, y is free, so we had z equals cx squared. If we change it, the equation, and we put z equals cy squared, now x is free, so it comes out the x-axis. And the last thing we could do I do it? Z equals x squared, y is free. Did I do the third one? I didn't do it. Where is it? I don't know where it is. Oh, there it is. Okay. X equals cy squared. There we go. That one, z is free, so it goes up the z-axis, right? All right. That's parabolic cylinders. Ellipsoids. All traces are ellipses. You cut it this way, you got an ellipse. You cut it this way, you've got an ellipse. You cut it this way, you've got an ellipse. What does that look like in three-dimensional space then? Looks like an egg. It's exactly what it looks like, an egg. So here it is. Here's your egg. Right? Doesn't matter how I cut it. Come in here, cut it with the plane that goes up and down. Right? Stop. And you're going to get all these little parabolas no matter where you cut. If I cut it with something in the YZ plane, like that, what am I going to get? More ellipses. Did I say parabolas? I think
No, I did.
Okay.
Yeah.
Okay. So cut it with planes this way, you get ellipses, right? Ellipses. And if I come in with the plane this way, I'm going to get ellipses also. So like in all three directions, you get ellipses. And this is an ellipsoid. This is an egg. Okay, so it asks us to sketch this one by hand. Oh, wait, you know what we didn't do? We didn't look at the equation of an ellipsoid. Back it up. Back it up. Look at the equation of an ellipsoid. Do you have a free variable in an ellipsoid? You do not have a free variable in an ellipsoid, right? So A, B, C, this looks just like an ellipse, right? It's just you have another piece here. So it's just like an ellipse. The A, B, and C are going to make it either be, taller or wider. Just it has an impact on those, on the shape of the ellipsoid. But when we look at this is the first time we've seen all three variables appear, right? X, Y, and Z all appear, and they are all squared, right? You have addition between all of them, and you have equals 1, right? So remember that, because when we look at something else now, we're going to see how the equation changes. I'm not going to do traces to sketch these by hand, all right? I'm just not. All right, how about an elliptic paraboloid? So traces of an elliptic paraboloid are ellipses and parabolas. So when we cut, we're either going to get an ellipse or a paraboloid. Or not a paraboloid, a parabola. And it always opens in the direction of the variable raised to the first power. Okay, let's take a look at one of these. There you go. If I cut this with this plane, what am I going to get? Ellipses, right? If I cut it with that plane, I'm going to get what? Parabolas. And if I cut it with this plane, I'm going to get parabolas again, right? So this is what makes an elliptic paraboloid an elliptic paraboloid. You get ellipses one direction, you get parabolas the other. And the equation is this. Here's the equation of an elliptic paraboloid. By the way, these are all in your book. All of these shapes are summarized on one page inside the textbook. And it is on, I think I say this in the notes where it is, but I'll just go ahead and tell you now. Page 578 has a summary, has a little picture. The pictures aren't that great, but it has a little picture and it shows you what all the equations look like. So if we have this, what is the main difference between this and what we just saw a second ago with the elliptic paraboloid? Not quite free. You still have all the variables, right?
You're solving for one.
One of the variables is raised to the first power, right? So instead of having like z squared over c squared, we just have like z over c. We also don't have that 1 in there, right? Right? It was like equals 1. We don't have that in here. We have variable squared over a number plus variable squared over a number equals variable over a number but not squared, right? That's what gives you that elliptic paraboloid, all right? Also, I say here, notice that the elliptic paraboloid opens in the direction of the variable raised to the first power. So when you go back and you look at this equation, notice that z is the variable raised to the first power, right? And notice that this elliptic paraboloid opens up in the z direction, all right? That's how you know that it goes like this as opposed to coming out at us or something. So I give you here the other examples. So look at this one right here. See this one? This is an elliptic paraboloid. So if I look at the equation of this, which variable should be to the first power? Y, right? So it should look like this instead. Make sense? And then if I do this, I could come out at us, right? X-axis. So if it comes out towards the x-axis, right, then the equation is going to look like that. Moving on. Hyperbolic paraboloids. We're almost done. There's not like 20 of these or something. There's only like about 8.
Just
Question.
Before you move on.
Yeah.
So like if it was like if it was the paraboloid like in the negative x, does that mean the term would be negative?
If it was the negative x,
Because let's say like the one that was the first power is positive, so it's coming out. If it was negative, it would be going out the other way.
well, it wouldn't. You couldn't have that because the other side of the equation is everything squared. So you couldn't have the right side. So you're only going. The only way to change that is to go and do negatives across everything. So that means no. Yeah, it would have to.
So does that mean the shape just doesn't exist on that side?
Exactly. Exactly.
Okay, thank you.
All right, good question. All right, so, what are we looking at? Hyperbolic paraboloids. So what, I mean, just look at the name, hyperbolic paraboloids. So you're thinking you're going to see hyperbolas when you slice one way and parabolas the other way. And it just becomes very difficult to visualize this, okay? So you just look at the pictures like there it is. It's a freaking mess. It's cool, but it's a mess. It's a really cool shape. It's like this weird sort of saddle looking thing, right?
I've actually seen these things before.
You seen these?
Yeah.
Yeah. So there you go.
It's like they curve negatively along the y-axis, the y-z plane, positive up.
Yeah, it's like you have like concave down here, but then you have like concave up here. It's like reversed. And we will actually we will study these later, and we are going to be looking for where this like weird point in here happens, and we call that a saddle point, but that'll be later. Okay, so here's this, what is this again? A hyperbolic paraboloid, so hyperbolic. So let's try and slice this. Here we go. Let's go XY slices coming through here. It might be easy to see this, maybe not. Do you see that if we look from straight up top, do you see that? You can see the hyperbolas, right? Do y'all see that? And so if I start to put a bunch of these slices together, we start to get those guys. And I think now if I look at it from the top, you can see a bunch of hyperbolas. Not as easy as the ellipsoid, right? The ellipsoid's pretty easy to see. And then we can come in and we can start slicing with that plane. Can't take those off. Let me move this plane. I want it this way. So when I cut through there, yeah, it's kind of hard to see it, but when I cut through, see when we look from the top, those cuts, but when we look at it from the side, those are all parabolas, aren't they? Okay, what's the equation? Almost identical to the one we just looked at, right? With one exception. Minus between two of the variables. Right? Minus between two of the variables. So there's very subtle little changes in the equation that have huge impacts on the shape of the graph, right? And so that's what we need to do when we're trying to do these problems, is try and identify. I'm going to give, the whole goal of this is I give you an equation and you identify what shape it is. That's the goal. All right, and then we can have the equation switch up. We can have, our x and z squared and then have y. Or we can have y and z squared and have it solved like with x being the first power.
So it's kind of like the saddle is going towards.
Yeah, and we're not really going to concern ourselves too much with which way the saddle points in this case, just that it looks like this, okay? All right, next one, cones. Well, a cone is, traces our ellipses and hyperbolas. I think we've all seen a cone. But now that we can, think about it a little bit different, when we slice it with XY plane stuff, what are we going to get? Circles, or because this cone doesn't have to be perfectly shaped, we're going to get ellipses in that. Well, it depends on Depends on the equation of the cone. But those look like ellipses, right? Sliced this way. And then when we slice it this way, get those out of there, we have, what, hyperbolas? It's like here, and then here's its reflection up here. So it's like one of them here, there, that's a hyperbola. And then here's another one with its reflection up there. What's the equation? Ah, shit. I mean, that looks like a lot of other things, doesn't it? Okay, you have two of your, all three variables appear, all three variables are squared, but this guy's isolated on one side of the equation, right? This is not the same as the x squared, y squared, z squared equals 1. X squared, y squared, z squared equals 1 was ellipsoid. Well, over a, sorry, you're right, it's a sphere, but I was referring to x squared over a squared, y squared over b squared, z squared over c squared equals 1. That's an ellipsoid. This one, we have one of the terms is on this side. And I do say that the cone does kind of extend out in the direction of the variable that's isolated. So in this case, z squared, right, is isolated, so it opens that way. And we keep going. It could go down the y-axis, in which case your y squared's isolated. You could go down the x-axis, in which case your x squared is isolated. They're all the same thing. We're almost done. A hyperboloid of one sheet. That's the name of it. Okay, a hyperboloid of one sheet. Traces are ellipses and hyperbolas. Opens in direction of variable with a negative sign. Ay, there you go. This has always reminded me of like a nuclear power plant, that that steam stack they have, right? And so when I slice it with xy plane stuff, I get ellipses. When I slice it like up and down like that, I get my hyperbolas. And if I go this way, still hyperbolas, right? Now the equation of this, that looks like an ellipsoid, except one of the variables has a minus on it. And that one right there, the one that has a minus, is the direction in which it opens. You don't have to memorize these, okay? You need to just be aware of them. That way when they come up, you can refer back to your notes and say, ah, yeah, this is that. And we can switch it up, make it come out the y-axis, so you'll see the negative is on the y. Make it go out the x-axis, the negative is on the x. Yeah? And the last one, the way we get the last one is to take this picture right here and imagine like making it like narrow, 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 skinny, and then just go to a point where you just like pinch it off and they break apart from one another. And then what you get is the hyperboloid of two sheets. So do you see that that's the problem we just did? Let me see if I can get this to change. I'm not sure I'm going to be able to make this. I think maybe with this. No, too big. I need to move them closer, but let's not worry about it. Do y'all kind of see that that's the... Oh, this looks really funky to me. Does that look funky to you? Something looks off there. Yeah. All right, all we care about is the equation. So what's the big kind of thing glaring out at you here? Yeah, you got two negatives, one positive, instead of two positives, one negative. But it looks a lot like the ellipsoid. All right, that's it. You can have it open different directions. Who cares? Let's do this example. Take this, reduce it to a standard form of one of the surfaces discussed in this section. Classify the surface, include any details about traces. Really, I just want us to classify it. That's all I care about. Can you tell me, is this an ellipse?